Hi everyone, my name is Tia, and this video is going to be all about the fundamental reasoning and logic behind derivatives. Going into calculus, I remember being intimidated of derivatives just because the word derivative sounds a little bit intimidating and imposing. But honestly, once you get these fundamental ideas down, you're golden. It's not even that bad. In the previous video, I introduced you to the tangent line. We found the equation of the tangent line to the curve at a specific point using limit formulas, general limit knowledge, and algebra. If you need a refresher, I suggest you review that video. I have it tagged in the info cards. Having a proper understanding of the tangent line will set you up to have a good experience with derivatives. Let's recall the limit formulas. Solving these limits will give you the slope of the tangent line, m. That slope of the tangent line, the m value, is the derivative at that specific x value. Although the word derivative sounds kind of imposing and intimidating, you've been literally taking derivatives without knowing, so don't be scared just yet. Although both these limit formulas are valid ways of finding the derivative at a specific point, we usually refer to the first one as the limit definition of a derivative. Let's take a look at this in terms of application and practicality. We have the position, s, described in terms of t, time. So s of t equals to negative 4.9 t squared plus 2t plus 6. And when we take the derivative at a specific point using our limit definition, in the denominator we have the change in time, right? And in the numerator we have some change in the position. So overall, this ends up becoming some change in position over some change in time, and that gives us velocity. So when we take the derivative at a specific point, we basically get the rate of change at that point, or the instantaneous rate of change. What if instead of the position function, we were given a velocity function? Then, in the numerator part of the limit, we would have the change in velocity, and the denominator part of the limit would still be the change in time since the independent variable hasn't changed. But then the result of the derivative instead would be acceleration. The derivative and the derivative at a point are two different things. The derivative refers to a general equation, so you have the independent variable t and the dependent variable v of t. But the derivative at a point refers to plugging in some value for t, and in return you get a specific value for the derivative. The derivative of this particular position function is negative 9.8 t plus 2. I'll be explaining the derivative rules in a different video. However, at this point it's important to note that the derivative is a general equation with the same independent variable and a different dependent variable. The derivative at a point would just be taking some specific time value and then just plugging it in to the derivative. So when I plug in 0 for time, I get that the velocity at time equals to 0 is 2. There is a catch though. There are some situations where you can't find the derivative at a point. So you can have a general equation for the derivative, but the derivative at that specific x value may be undefined. The first case is if that the function is not continuous at that x value. So that means that there may be a removable infinite or jump discontinuity. The second case where the derivative can be undefined at a specific point is if there is a cusp or a corner at that point. A common place where we see corners is absolute value functions. The graph is increasing or decreasing, and then it immediately switches to the latter at a specific point, and it creates this sharp corner. Both of these functions are not differentiable at the a values. The third situation is if the tangent line to that point is vertical, which means it goes up and down. This is not to be confused to when the derivative equals to 0 and the tangent line is horizontal. There is so much notation for derivatives, so I'm going to go through a few of the popular ones and then you can just pick your favorites to use. The first one is f prime of x, or f prime, and it looks like f has an exponent of 1, but that's actually not an exponent. It's better labeled as a tally. So one tally is the first derivative, and as you go to make more derivatives, they'll represent the second, third, fourth, fifth derivative. The notation for an inverse function is very similar because it has a negative one. But these two are very, very different things, so it's important to not to confuse them. The next form of notation is y prime, where y, or whatever letter that you use, represents the dependent variable. I'm not a big fan of this form of notation because it doesn't denote or specify what the independent variable is, which is very, very important. The third form is one of the more popular notations. It's DYDX, where the d's represent delta, which mean a change, and in the numerator you have the dependent variable, and in the denominator you have the independent variable. People often write df dx2, which is essentially the same thing. The next one is ddx of f of x. I'm not a big fan of this one either because it's a bit clunky, and when you do many lines of work, your page can get a little bit messy. All these ways of representing the derivative are equivalent, but some of them clearly have advantages over the others, so choose your favorites and whatever works best for you personally. That will be all for this video. Thank you so much for watching. I hope that it was enjoyable and informational, and if it was those things, please like this video and subscribe. And as usual, if you have any questions, please leave them in the comment section.